Every year, more than 50 million people around the world are adversely affected by road accidents. 1.35 million people have their lives cut short, and a large proportion of the affected suffer serious, long-lasting injuries. And the effect isn't limited to human cost. The WHO estimates that most countries lose 3% of their GDP as a result of road accidents alone. A close examination of the cause of road accidents paints a surprising picture. A large proportion, from 20 to almost 50% of all accidents, are caused by drowsy drivers. And while vehicle manufacturers have tried to combat this by introducing attention alert systems, the cost of these vehicles makes it unattainable for the vast majority of the affected. 93% of road fatalities happen in low and middle income countries. It is this problem that we aim to address with Drow-Z. Drow-Z lays the foundation for a computer vision-based drowsiness detection and alert system. It reads the feed from the vehicle's camera and sends an alert when it detects that the driver is drowsy. And it works locally, so there's no need to worry of the feed making rounds in data warehouses. The system is resilient to variety in drivers' faces and needs a closed-eyed image of the driver for calibration. It uses a combination of eye aspect ratio detection and motion detection to determine whether or not the driver is drowsy. The motion detection makes it so that even if the driver's eyes are obscured by sunglasses or in any other way, the system still works as per the driver's needs. The thing that we need to look out for in real-time systems like this one are false negatives. So the instances where the driver is drowsy but the system cannot detect it. We saw no false negatives in our testing of this system, and the false positives where the system detected drowsy drivers in cases where there was no drowsy driver, these false positives were few and far between, happening half a dozen times during the entire process. We followed a Scrum-like framework of development, dividing the main script into 3 modules, with one person working on each module for 4 hours every cycle before sitting down in a huddle to discuss the results and the problems. Each huddle lasted for about an hour, where we collaboratively identified and fixed problems and discussed iterations to make the system better. We built a simple eye blink based system in the first few cycles and then iterated it to a system that adapts to different faces, and then we added motion detection to it in the subsequent cycles that followed. In the end, we integrated everything into a single cohesive system. The major problem that limited us was that of time and hardware. We could not train a face detection model on our own due to these limitations, and we resorted to using a pre-trained model. If we had more time, we'd have built a better face detection model and optimized it. The other thing that we'd have done if we had more time was to include more face variety in the testing process. Color spectacles that obscure the eyes in multiple faces have been documented to cause error in the operation of similar systems in the past, so more time for testing these fringe cases would have made the system more robust.